Hello. As Tara was saying, I'm Steve Thomas. You may know me as Scoops. I've been doing this for half my life, 14 years. So, yeah. So, it's a little busy, but basically these are, so the hashing algorithms, or well, the authentic, or storing passwords, whatever. They have hardness levels. Basically, if we put them all on the level playing field, such that like they all take 100 milliseconds or like 12 years or something, this is how they'd be ranked. Some of them are actually, you can't change the hardness. There's scrypt, selectable no memory, then bcrypt. That would be a good one. Oops. Bcrypt, it uses a 14 kilobyte internal storage, which makes GPUs slow. Not really, really slow, but it's, so that's a good algorithm. PHPass and SHA-2 based crypt. These are all, and also, these are all like a class of sequentially hashed hashing algorithm type things. Basically, you have your password and salt, and then you hash that. Then you take that value, and then you hash that with the password or some salt and stuff. Then you just continue a long line of that. There's actually two different classes. Ones that use 64-bit and 32-bit. The 64-bit ones, such as SHA-512. So the Defender has usually a 64-bit processor, so they can do these really fast because it's all native. With SC2 or other vector instructions, it basically cuts the amount of instructions that you can, operations that you can do per instruction in half. So the attacker has to take twice as long. And GPUs are also 32-bit, so they have to run at, 2 or more instructions just to one. PBKDF2. Basically, it's I would say it's bad because no one implements it correctly. Basically, it's actually, you should be implementing PBKDF1 for storing hashes because, like with Microsoft, they did PBKDF2 with SHA-1 and then 256 bits of output. So the first 160 bits is generated independently of the other half. So the attacker just focuses on the first half. Also, the attacker is definitely going to do cached HMAC, which cuts the amount of instructions in half. I don't know how Microsoft implements it. MD5 crypt, it's a static 1,002 rounds of MD5. That's bad. Single hash, this is usually unsalted. There's, double MD5 or triple MD5. Those are all in this. They're extremely fast, so that's bad. Actually, that's a thing. That would be fair. Almost anything with DES that's like LM and DES script, those actually truncate the key space so that it's extremely fast. And also the other ones, there's a couple that they only output 64 bits, so you can generate collisions sometimes. So that's it. MySQL 323. If you went at the beginning of this one, talk2.com/passwords12, it has all the slides currently. A while ago, I released a program that did a meet in the middle attack. Basically, MySQL 323 was an algorithm that they just came up with. Like MD5 would have been better. But what it does, my attack is, you start basically you fill your RAM with the first half of generated passwords. So you just generate the first half, then you take the hash and then step backwards to this meet point. And when you look up that value in memory, it effectively checks all the hashes that you pre-generated and with the end. So you can get quadrillions of hashes per second. You can find a collision in a couple minutes. It's a 62-bit hash. XSHA-1. This was Battle.net's attempt, or well, implementation of SHA-1. They messed up. Basically, instead of rotating n by 1, they rotated 1 by n. So there's only 32 possibilities. So you can brute force 2 to the 61 passwords per second. Single core CPU. Public service announcement, why you shouldn't use LastPass. So they recommend 500 rounds of PBKDF2. They actually do it correctly. They use well, it's for encryption keys, so it's good. But they recommend 500 rounds of PBKDF2. 12 years ago, when it was standardized, the recommended was twice that. The URL field is unencrypted, so they know what sites you have accounts with. Now, HushMail, if you're not familiar with, they basically were asked to disclose, it was a program, a web program for email, encrypted email, and they were asked to basically get the encrypted keys from users, and then they injected JavaScript. Well, the attack with LastPass is there's this error code when you log in of iterations. So they could set it to 1, and then it's just double SHA-256, their old algorithm they were using. Then when they get that, then they can say iterations, 500, then the user doesn't even notice that they just sent double SHA-256. Basically, the user will just see, it took twice as long. Internet's slow. Just use KeyPass in Dropbox or Google Drive, or host your own LastPass. I've told them over a year ago about this. How much salt and pepper do we need? Well, I was told by Soler, designer, that I should only refer to salt as the cryptographic salt for hashes. Basically, it's a random number, or random salt that is per hash. Basically, there's like cryptographic salt and uncryptographic salt, which that's kind of how I consider it, so I just say salt. But, pepper, I guess that would be our uncryptographic salt, such as the first one, a public pepper for logging in. So when you're logging into a service, instead of giving your plaintext password, you give a salted password that is only for that one site with your username. This doesn't really work for web pages because JavaScript comes in. They can actually just get around that. But this is so that if someone roots the box and then starts, they basically inject code to dump whatever comes in, they don't have your plaintext password, so they still need to crack it. Then private salt stored in the database, you can't have targeted, pre-computed attacks. Encryption keys stored on the authentication server, so that's salt or pepper, but basically when you dump the database, none of your hashes are worth anything, unless they also break into the authentication server. This is also called local parameter. Site-specific ROM. This is just terabytes of random data. A salted password gives you an offset into the file, and then you use that with your salted hash to then hash that for comparing. Basically, the attacker has to download a large percentage of the data before you can start cracking the password. Basically, if you get like 1% of the database, or the ROM, then you can only crack 1% of the passwords that you were able to download from the database. Easy detection of intruder, so your bandwidth is like, It's going to be kind of obvious. Also, if the server has a 10 megabit NIC, then just the bandwidth constraint means that you could do about 4,000 authentications per second, and it will take over 9 days per terabyte. So what to do about password hashing algorithms for authentication? There should be a NIST-sponsored competition for PBKDF3, and we all know who's going to win that. Is he still here? No. Okay, whatever. So there should be a standard for storing credentials, like the $1, or whatever it's going to be. Forced minimum iteration count. Basically, it's to prevent companies like BlackBerry or RIM to say, we're secure, we do PBKDF2, and then in fine print it says 1 iteration. Upgrade paths without the password. This is so that in 2 years you can increase the strength of your passwords without needing everyone to log in or change their password. Parallel and memory hard. I'm thinking there should be like one that's parallel and one that's memory hard, because or some combination of both. That's what the competition is for, to figure this all out. Basically, parallel versus memory hard. The more parallel you are, the less memory hard you are, unless you start using like insane amounts of memory. My best effort. Basically, this is just for the parallel side. scrypt already got the memory hard stuff, so you don't really pay attention unless you got the slides. So you can use. Pros and cons. Force minimum iteration count. Basically, I multiply the iteration count that you're given by 2,000. So 0 iterations would be, it wouldn't do anything. And then 1 iteration, then it's 2,000. There are, you can just say, if it's less than this number, then you don't generate a hash. But people just, those are just recommendations. Parallel, so basically you could send this to GPUs for authentication. If you have like a high-end GPU and you have to take 10 milliseconds on that, if you have, let's say, 25 GPUs, it'll be 2,500 per second. Upgrade path without the password. Those 3 bullet points. I haven't found one algorithm that actually does any of those. The only problems is no site-specific ROM unless you do it at the beginning, which means that it's less efficient. Or you can do it in the middle, but then you have to modify the algorithm. Not memory hard unless the hashing algorithm, the hash, is actually memory hard, such as like bcrypt with a hardness of 0, which is 2 to the 0, which is 1 iteration. So it would be as hard as bcrypt 11, which isn't really feasible right now. But with AVX2, that's going to add some instructions such that you can do bcrypt nicely parallel. That's about it. Questions? Questions?
So I know that you were pushing for a parallel password derivation function. It seems like going serial would be better in terms of slowing people down. It doesn't. It wouldn't just go wide essentially. Why do you prefer parallel over serial for password?
Okay. The reason why parallel is better, the attacker can try 20 billion passwords in parallel if they wanted to, assuming they had hardware for that. The defender, if they can only do serial, then they can only do 1. So with AVX or SC2, you can do 4 4 in parallel per thread, and that's increasing to 8 next quarter, I think.
Okay, so basically you're allowing the defender to make more effective use of their hardware to give the attacker less of an edge.
Yeah.
Okay.
Basically, it's just a ratio between attacker speed and defender speed.
That
And
makes
if they're
sense.
both parallel, then they're running the same code, basically. Any other questions?